Hello, welcome to another video on gPROMS. Today, we are going to look at how we can solve the mixing tank problem, the buffer tank problem in gPROMS. So here is a schematic of the tank. You have inflow into the tank. So the flow rate is F in at the inlet, and the flow rate is F out at the outlet. And the H represent the level, the liquid level in the tank. And M represent the hold up in the tank. And this is a stirrer, and is well mixed. And that's what we can make assumption of this well mixed assumption. And isothermal operation is also assumed. Now we have the mass balance. These are the equations that we want to solve. The mass balance equation and the relationship between mass hold up and the level. So given as area multiplied by height multiplied by the density, and the relationship between the outlet flow rate and the level. So F out equals alpha square root of the height. Okay. You have some data here, the cross-sectional area, density, the alpha, F in, and the initial level and the tank. So to solve this problem, we perform a degrees of freedom analysis. So by counting the number of equations that we have, the number of variables, to see if we need specifications to be able to solve the problem. Now for the first equation, equation 1, we have, so if we count the variables that are involved, we have F in, F out, and M, so 3 variables. And you can have them here. Number of variables, number of equations, it's just one equation. And for equation 2, we have M has been counted already. A is a parameter, rho is a parameter. So the only variable we have here is height, H. So H is there. And you have just one equation. So one variable, one equation. One variable, one equation. Then equation 3, so F out has been counted before here. Then alpha is the parameter. So H has also been counted before here. So there's no new variable. So we have one equation. So if we add all the equations together, we have 3 equations in total. Then we have 4 variables. So which means if you do the degrees of freedom analysis, using the number of variables minus number of equations, 4 minus 3 is 1. So we need to make one specification to be able to solve the problem. So one specification, what do we know? So usually we use the known values of the variable, like what we know coming into the tank. So we know the flow rate into the tank we're given in the problem statement. So we can specify the flow rate into the tank, F in order to make the degrees of freedom 0. Now let's see how we can implement this model in gPROMS. Here is the buffer tank model. So I already created the variable type, length, mass, and mass flow rate. So the model, the buffer tank model, is very expanded. So I declare the parameters, density, area, and alpha, which is the valve constant. And I have the variable M is the hold up. So F in is the inlet flow, F out is outlet flow, and H is the height. So, and these are connected to the various variable types. Okay, so I recommend you are more descriptive in your code. So you can write the full hold up here, flow in, flow out. So that is highly recommended. I decided to make this like this, so to make the code like easier to read for the viewers. Okay. Then the equation, the mass balance equation, we have M dollar sign M because we have derivative of the hold up equals F in minus F out. So that's the equation 1. And equation 2 is this, M equals area times height times rho. And equation 3 is this. So F out equals alpha multiplied by square root of the height. Okay. Now, if we go to the process, the first thing we do is to create a copy of the model. So we call it tank as buffer tank. So this is the name I'll be using in this process. This is the name of the model created. Then set the values of the parameters. There are 3 parameters. So the area, the density and an alpha, and assign the degrees of freedom. Remember, degrees of freedom is 1. We need to make 1 specification to be able to solve the problem. So that's F in, specify the value of the F inlet flow as 10. And because we have 1 differential equation, we need 1 initial condition. So here we are using the tank, and we're specifying the height, the liquid level of the tank at the initial stage of the process. The reporting interval, I can specify that on that solution parameter. This is not mandatory here. You can also do that in the dialog box that will pop up when you run the code. So you can put 1 here. And the schedule is where we specify the operating procedure, then how long we want to run the simulation for. Then if I run it, as you can see, the reporting interval is already captured. And okay, then I have the result. So by expand that result case file, result trajectory tank variables, then I can check how the height changes over time. You can see the level increases over time for the period that we run, and the hold up as well increases. Okay, so that's how to solve the buffer tank model with gPROMS. So I hope you find this useful. If you are new to this channel, don't forget to subscribe and hit the notification button to get notified of my new videos. Thank you very much for listening. If you like this video, um, please check the like. If it's a thumbs up. Thank you, and I will see you in the next video. Bye-bye.